Hello, welcome back to Educator. Next we're going to continue with our NMR lesson to learn about some more advanced NMR facets, to learn how to interpret an NMR spectrum, and also to get into a little of carbon-13 NMR spectroscopy. So let's talk about some problem-solving strategies we can use when given a proton NMR. How can you go about determining a structure from it? Three basic things we need to accomplish are: first, determine what pieces are present. Okay, what we're going to be doing is very much like building a puzzle. And so the first thing we have to do is figure out what puzzle pieces there are. Then we have to figure out how to put those pieces together. And when we're done and we have a structure that we'd like to propose as an answer, what we're going to do is we're going to confirm that the structure does in fact match the spectrum. We're going to use those skills that we did in being able to predict an NMR spectrum given a structure and confirm it. So what's great about NMR is when you have the right answer, you know you have the right answer, and you can breathe a sigh of relief and move on. Okay, so here are the steps we're going to take. The very first thing we need to do is, if we're lucky enough to have an IR spectrum provided to us for our molecule, then we're going to analyze that spectrum for any functional groups that might be present. Okay, a lot of times spectroscopy problems are given in combination, so you'll get maybe an IR spectrum and a proton and a carbon NMR, and so the more data you're given, great, work with it. So let's take a look at the IR, see if we have things like, a carbonyl is really obvious in the IR, somewhere around 1700. We find that very strong signal. OH groups are very obvious in the IR, those broad peaks around 3300. Right, we can look for the presence of double bonds, hydrogens on those triple bonds, and so on. Okay, so those are going to be pieces to our puzzle. Those have to be incorporated into our final answer, into the structure that we have. Okay, the next thing we're going to do is we're going to look at our molecular formula. If it's provided, if we're lucky enough to have our molecular formula, we're going to analyze that and determine how many degrees of unsaturation we have. Now what we're going to do is we're going to look for the formula C to the N, H to the 2N plus 2 is the formula we expect if we have a saturated molecule. If we have any nitrogens present, we need to account for those by for every one nitrogen, we need one extra hydrogen in our structure, so we can modify our formula a little bit to accommodate those. Oh, I'm sorry, 2N plus 2. See that I missed my N there. So twice the number of hydrogens plus 2. Okay, and every two missing hydrogens gives us a clue to our structure, because it tells us we have a degree of unsaturation. That means we must have a double bond, or we must have a ring to account for those missing two hydrogens. Okay? If we happen to have 4 or more degrees of unsaturation, then it might be possible a structure as a benzene ring. If you take a look at a benzene ring, we have a 6-membered ring with alternating pi bonds. Okay, so that means we have 3 pi bonds plus 1 ring. That equals 4 degrees of unsaturation. That means if we have 8 missing hydrogens, then it's possible that we have a benzene ring in our structure. That's a great way to account for a lot of degrees of unsaturation very quickly. If we do not have 4 degrees of unsaturation, if we have fewer than that, it's impossible to have a benzene ring in our structure. So really, the molecular formula is telling us something very significant about our structure. Okay, the next thing we're going to do is we're going to draw out the various pieces to our molecule. We're going to be using the peak integration, the size of each peak, to tell us how many hydrogens there are in each. Okay, so for example, if you see a signal that has 3 hydrogens in it, let's assume that's a CH3. Okay, because it's possible to have 3 hydrogens coinciding some other way other than a methyl group. But if you hear off in the distance, if you hear something galloping, you hear hooves beating against the ground, you should probably think in terms of horses before you imagine that they're zebras. It's possible that they're zebras, but let's go with the more obvious choice, the more likely choice. Okay, so a 3 hydrogen signal means we probably have a CH3. A 2 hydrogen signal means we have a CH2. A 1 hydrogen signal means we have a CH, or maybe an OH or an NH if we have those elements in our formula. Okay, a 4 hydrogen signal is a little trickier, not as common, but obviously there's not a CH4 puzzle piece. So maybe we have 2 CH2s that are chemically equivalent, therefore giving rise to one signal, or maybe a CH3 and a CH that can't be chemically equivalent, but they might just be overlapping because they have the same chemical shift. So there may be some more complex things, but we'll come across that. We'll deal with those when we come across them. If we have peaks around 7 parts per million, we're going to assume there's an aromatic ring, a benzene ring. Okay, it might just be a single peak. Very common if they're very similar in their chemical environment, then they're going to have the same chemical shift. Or you might have several signals in the region around 7. Okay, we're going to look at all the signals that are around 7, and we're going to see how many total hydrogens there are. If we have 5 hydrogens around 7, that means we have a monosubstituted benzene ring. So in other words, the piece to our puzzle is a benzene ring with something attached. Okay, that means if you attach one thing, so we have a monosubstituted benzene ring, that means you have 1, 2, 3, 4, 5 hydrogens left, and those are going to show up in your NMR. Okay, if you have a total of 4 hydrogens around 7, that means you have a disubstituted benzene ring. So this is monosubstituted. Disubstituted means that you have a benzene ring with 2 things attached. Where are those 2 things attached? They could be para or ortho or meta or para, but you have only 4 aromatic protons, meaning 2 of those positions are occupied by something other than hydrogen. Okay, so we're going to do this to come up with all the pieces in our puzzle. And then the next thing we're going to do is we're going to confirm our pieces and make sure, before you start building your molecule and putting your pieces together, you better make sure you've come up with all the correct pieces. So what we're going to do is we're going to add them up, and we're going to make sure that they match the molecular formula. Okay, the way you can do that is to make sure, have you accounted for all the degrees of unsaturation? If you said there were 2 degrees of unsaturation, do you have 2 double bonds in your pieces? If not, know that you still have to incorporate a ring when you put those pieces together to get that second DU. Have you accounted for the functional groups in the IR? If the IR told you you had an OH, then one of the pieces in your puzzle needs to be an OH. Okay, so we're going to confirm that we have all the pieces present. Now we're ready to start putting them together. Okay, how do we decide which 2 pieces are connected? Well, we're going to consider the chemical shift. Is it electron rich, electron deficient? We're going to consider the splitting pattern. Does it have any neighbors? Okay, and we need to consider both of those. So the easiest thing is to start with an end piece, like a methyl group, and start to see what things we can attach to it. Okay, for example, if it's next to an oxygen, I could attach it to an oxygen if its chemical shift is around 3.5. Maybe it's next to a carbonyl or a benzene ring if its shift is chemical shift around 2.2. So we'll consider where it is on the spectrum to decide who it's next to. And we're also going to consider the splitting patterns. If it's a triplet, that means it must have 2 neighbors. So I'm going to find a CH2 piece and I'm going to attach it to that. Okay, so bit by bit we're going to take all these different pieces and start hooking them together until we come up with a complete structure. Before we're done and we pat ourselves on the back, we need to go back and check our structure. This is the last step in our methodical process. Does it match the molecular formula? Sometimes when we start working, if we spend a long time on a spectrum, it's easy for a piece to fall off and never get added back on. And then you think you have the solution, you realize you're missing some carbons or oxygens or nitrogens. So does it match the molecular formula? Does it match the functional groups in the IR that you predicted? Does it match the NMR? Remember, we worked on how to predict an NMR spectrum. How many signals are you expecting? Is there the symmetry in the molecule that's required to get the right number of signals? What would the integration be for each peak? What would the splitting patterns be? What would the chemical shift be? Okay, so that's our very last step is to confirm that we have, in fact, determined the right structure. So let's try some problems. Okay.